Welcome back to another deep dive. You know how we're always getting requests to compare TCP/IP and OSI? Well, today's the day we tackle those two big network models.
Sounds good.
We're assuming you already have a handle on the basics of computer networks, data, that kind of thing.
Yeah.
But we want to take you deeper. Imagine data zipping around online, like a letter in a pneumatic tube system.
Okay.
But instead of one long tube, picture layers of tubes, each with its own set of rules.
Right.
And that's kind of what TCP/IP and OSI are, like blueprints, making sure different systems can understand each other.
I like that analogy.
Oh, and get this, we'll uncover how old cable TV tech is now key for your internet.
Huh. Interesting.
And did you know some network layers can swap without others even noticing? We'll get into all that.
Oh, I'm ready when you are.
Okay, well, right off the bat, one of the biggest things both models stress is clean interfaces between layers. And I found this quote in Computer Networks that explains it. When network designers decide how many layers to include in a network and what each one should do, one of the most important considerations is defining clean interfaces between the layers.
Yeah, that's a good one.
So help me out. What's that mean in practice?
Okay, so picture building a house. You wouldn't want the electricians messing with the plumbing, right?
No way.
Each person has their job, and as long as the points where their work intersects are, clear.
Like the wiring near the sink.
Yeah, exactly. One can be swapped without affecting the others.
So it's all about making sure each layer can do its job without messing up others.
Exactly. And for a system as complex as the internet, that is huge. It lets different technologies work together, and it makes upgrades easier without breaking everything.
Makes sense, like swapping phone chargers. As long as the plug fits, the phone's happy.
Exactly. Now, let's talk about connection-oriented versus connectionless service. This is where TCP/IP and OSI really show their differences.
Okay, remind me again, what's the difference between those two?
Imagine you're sending a package. Connection-oriented is like a dedicated courier. You know when it arrives, delivered in one piece, just like you sent it like a phone call. Continuous and unbroken.
Like a carefully planned convoy.
Yes. Connectionless is more like sending a postcard. Might take a different route, arrive out of order, might even get lost. Each piece travels independently, receiver puts it back together.
Ah, so that's how the internet handles so much traffic. It's not micromanaging every single piece of data.
Exactly. A key advantage of the TCP/IP model, being mostly connectionless at its core, super efficient for handling the internet's crazy data flow.
Makes sense. So how does this play out in the actual layers?
Let's start with the physical layer, the foundation. We're talking about the actual cables, signals, connectors.
Like those coaxial cables, the ones we used to use for cable TV, now used for internet.
Right, repurposed for a new age. And what you choose, copper wire, fiber optics, wireless, it all affects performance. Like streaming a movie over dial-up versus fiber optic, it's like a bike versus a bullet train.
Huh, I get it. But no matter how fast, there's always a chance of errors, right? How do these models deal with that?
Error correction, like a spell checker for data. By adding redundant bits, check bits, the receiver can spot and even fix errors during transmission.
A safety net to make sure the data arrives okay.
Exactly. Super important for reliable data, especially when things get unpredictable. So think about downloading a huge file and your internet just dies.
Ugh, the worst.
Right. Without some kind of traffic management, it would be chaos.
Like trying to fit an orchestra through a revolving door.
Exactly. And that's flow control, making sure data transfers smooth, even with different speeds. It's like a traffic light system for data packets, no congestion, no lost data.
So it stops the sender from overloading the receiver.
Right. This is another area where TCP/IP and OSI are different. TCP, built-in flow control. OSI, different layer, more flexible, but also a bit more complex.
So like a streamlined express service or a slower, customizable delivery.
Exactly. Now, talking about delivery, let's get to routing. How data finds the best path through the network.
Right, because data packets don't have their own GPS, do they?
I wish. We use algorithms to find the most efficient route through the internet maze.
I've heard of Dijkstra's algorithm. Does that come in here?
Absolutely. Classic algorithm, used for ages to find the shortest path. Think of planning a road trip, fastest route, traffic, roadblocks, speed limits, all that. Dijkstra's algorithm does that for data packets, finding the best path based on live network conditions.
So like a smart navigation for data, getting it to its destination fast.
Exactly. Essential for everything, loading web pages, video calls without lag.
Okay, so we've got flow control for speed and routing algorithms for the best path. What else?
Security. Super important nowadays. That's where encryption comes in. Scrambling data to keep it safe.
Like a locked safe only the recipient can open.
Perfect. Different ways to do it. Symmetric encryption, same key for encrypting and decrypting.
One master key for the safe.
Exactly. But what if you got to share data far away? Can't just hand over the key. That's where asymmetric encryption comes in. Two keys, a public key for encrypting, anyone can have it, and a private key for decrypting, kept secret.
Like a mailbox. Anyone can drop stuff in, only you have the key to open it.
Exactly. Asymmetric encryption's the backbone of online banking, e-commerce, all that.
Good to know. But encryption's just one part, right?
Right. There's also authentication. Got to make sure it's really the sender, and the data's untouched. That's where digital signatures come in.
I've heard of those, but how do they work?
Think of signing a document. Your signature, it's unique, hard to forge. Digital signatures do that digitally. A fingerprint for a message proves it's real and hasn't been messed with.
A tamper-proof seal, so the recipient knows it's really from you and hasn't been changed.
Exactly. Digital signatures are vital for trust online, especially for money stuff and legal things.
It's wild, all this stuff happening just so we can browse the web.
It's a lot, right? And we haven't even touched on streaming, gaming, mobile apps all have their own challenges.
So much to talk about. But let's stick to the core stuff for now, how it all fits into TCP/IP and OSI. What's next?
Let's see how these functions fit in the layers of both models. OSI has 7, TCP/IP has 4. Each layer has its own job, working together to transmit data safely and reliably.
Like a team, everyone with their role to achieve a goal. But how do the layers actually differ?
That's the cool part. They both do the same things, but they organize them differently. OSI, separate layers for physical and data link. TCP/IP combines those into one network access layer.
So one's more detailed, the other's more simplified?
Yeah. OSI, theoretical, complete, and flexible. TCP/IP, practical, efficient, gets the job done.
So which one's better?
Well, it depends. OSI is a great model, common language to understand networks. But in reality, TCP/IP runs the internet. It's simple, strong, and it works. It's become the standard.
Like comparing a fancy drawing to the actual blueprint of a house. One's the idea, the other's the real thing.
Exactly. OSI has had its influence, but TCP/IP makes the internet work, connecting us all.
It's amazing, all this complexity, and we don't even think about it.
True. But there's more, especially in the higher layers, the protocols and applications we use.
I'm ready for more. Okay, so those higher layers, this is where we see the stuff we use every day, right?
Yeah, it's like we built the roads, and now we're looking at the cars, the actual things transporting the data.
So email,
Yeah.
I use it constantly. How did that fit in?
Email uses SMTP, Simple Mail Transfer Protocol. It sends your messages to the recipient's mail server. Think of it like a postal worker, takes your mail and delivers it to the right place.
Simple, huh? I hope it is.
Well, SMTP is simple on purpose. It relies on TCP to make sure those messages get delivered completely and in order. TCP does all the hard work with error checking and stuff.
So SMTP delivers, and TCP makes sure it gets there safe.
Exactly. How different layers work together.
Makes sense.
Yeah.
But what about something like streaming video? More real time. How do those protocols fit in?
Streaming video. Oh, that's a whole different challenge because you need data flowing constantly, no delays. That's where RTP comes in, real-time transport protocol.
RTP. How's that different from TCP?
TCP is great for reliable delivery, but it can be a little slow. Fine for email, but for video streaming, you don't want delays.
Yeah, nobody wants a movie where the sound's out of sync.
Exactly. RTP is all about speed, minimizing delays, and jitter keeps everything smooth, like a high-speed lane for your video, no traffic jams.
So RTP is all about speed, and TCP is about accuracy. Like a sports car versus a truck. Depends what you're carrying.
Great analogy. Which brings us to another thing. How does data find the right place? The internet's massive. Gotta navigate that somehow.
Data packets don't have their own GPS.
No, they don't. We use DNS, the domain name system, like the internet's phone book. Turns names like google.com into numbers, IP addresses, so computers understand.
So I don't have to remember a bunch of numbers. I just type google.com, and DNS does the rest.
Exactly. DNS is everywhere. Make sure you can always find the website you're looking for. Really important part of how the internet works.
Wow, it's mind-blowing how all this stuff works together just so we can use the internet.
It is pretty incredible, all thanks to the people who designed and built it. And it keeps changing as technology evolves. These models, protocols, they're always adapting.
So we covered a lot, from cables to the apps we use, all thanks to TCP/IP and OSI.
Yeah, we follow the data all the way through the internet.
Big thanks to you, the listener, for sticking with us through this deep dive. We hope you learned something new about the internet. It's a pretty awesome thing, connecting us all. That's it for today. Keep exploring and learning. See you next time.